It's okay if you read it too. I know some people read it.
Today we are going to be talking about the deformation of 2D and also 3D shapes in real time. Typically, user manipulates some control handles like points or regions. Very often, a user might want to add some more handles on the deformed shape, such as on the ears of the armadillo. It seems simple, but previous method does not support such fast redefinition of control handles. Let's look at the pipeline of previous method. The user first needs to specify the control structures like a skeleton. And then compute the corresponding weights for it. Finally, the users could start the actual fun part of deforming the shape. If handles are changed, the user really needs to start from the very beginning, which is inefficient because the computational weights is slow using previous automatic weights. Our method breaks the pipeline by allowing the user to iterate between defining the handles and also deforming the shape. In this example, the user first deformed the shape. Here the user adds the new handles onto the tongue of the score, and the weight is recomputed immediately. It took about half a second for our method to recompute the weight. Again, here the user wants to add some more handles on the ears of the score, and also it computes very fast. Our method breaks much of the recent work on real-time shape deformation has focused around two families of methods. The first one is generalized Bayesian coordinates. It requires a cage that is designed to be adaptive to the input shape. And we then compute some coordinates. Deformation is driven by translating the cage vertices. The deformed vertices is simply a linear combination of all control points weighted using coordinates. One limitation for generalized Bayesian coordinates is that the coordinates are actually cage-aware instead of truly shape-aware. So this means the user really needs to carefully construct the cage, which is a burden to the user, and also the user can only specify rotations. And the user can only specify translations, no rotations directly supported. Another popular linear deformation model is linear blend skinning. And user needs to specify the influence of each bone, the weights. Shape vertices are transformed using a linear combination of bone transformations, weighted using bone weights. Linear blend skinning always requires full transformations to be specified even at point handles, which could be unintuitive. And also existing automatic weights could be slow to compute. So let's move to our method, in which we would like to unify these two methods together. So we consider a family of deformations that minimize the quadratic energy, the choice of x transpose A and x. So the choice here is that we simply do the optimization for x, y, and z dimension independently. And x is an n by d matrix stacks positions of all mesh vertices. The n is the number of vertices, and d could be 2 or 3. So the first column of x stacks the x coordinates as the second for y, and there will be one more if in 3D. We minimize the quadratic form subject to an interpolation constraint. So this constraint is really nothing but saying that there are some control points, some isolated vertices being repositioned at runtime. And also there are some control regions, some groups of vertices whose transformations are specified at runtime. And we use the matrix H stacks all control variables. And also we have the S is a binary selecting matrix. Selecting rows corresponds to control vertices. And also we have this J is simply doing a conversion from control variables to positions. Because we minimize the quadratic energy subject to a linear constraint, the solution will be linear to the control variables h, denoted as v equals w times h. Again, this w is what we are going to change at runtime, and h is what we are going to change, and w is pre-computed with matrix whose columns correspond to the handle's influence onto all vertices of the mesh. Well, there's no surprise that the energy matrix A should not be arbitrary. Obviously, the energy matrix should be positive semi-definite, and there are two other conditions not so obvious. The first one is the constant precision, which says that the constant vector should be in the kernel of A, and also linear precision, which says that the response V should be in the kernel of A. So these two conditions really come from the fact that we require the matrix A to be a deformation energy. Well, all you need to remember is that we must ensure this constant and linear precisions to make matrix A, to make it qualified for deformation energy. So surprisingly, there is no previous method achieves all of them, and we would like to modify an existing energy to have these two conditions. The one that we are going to modify is the squared Laplacian energy, which should be a natural choice because it has a quadratic form and it gives smooth displacement. It gives the smooth displacement field shown by previous work. So let's review what it is. We start by adding function x to be defined on each vertex of the mesh, and we construct L, the Laplacian matrix, and also M, the mass matrix. First, we apply the discrete operator to approximate the Laplacian of x, denoted as delta x. And then we compute the weighted norm of delta x. So this weighted norm is the so-called square Laplacian energy. The energy is saying that the function should be as harmonic as possible in the least square sense, weighted by the mass matrix. But we cannot use the usual Laplacian from previous work. Here we minimize the quadratic energy with some black points to be constant. If we choose the matrix A to be the previous square Laplacian energy, like either volumetric or sufficient Laplacian, we see that the response is lost. In the paper, we have little proof that the loss of response is due to the lack of linear precision. So that means this two Laplacian does not have the linear precision property that we want. So let's find out why. First, we notice that the matrix A and the Laplacian matrix L has the same node space. So we can just focus on the Laplacian matrix L. To trace where the issue is, let's just do a simple experiment. We have this nest shape, which is a 2D domain with an irregular boundary. We define a linear function f, which simply to be the x-coordinate at each vertex. And we compute the cotangent Laplacian. Then we can feed the function f to the operator L by multiplying them together. And we visualize the output. And you can see that the output is exactly 0 for interior vertices, but it's not for vertices on the boundary. Well, let's analyze why. The familiar cotangent Laplacian is assembled by first simply looking at the wandering neighbors for each vertex. For each hij, we will use the opposite angle alpha and also beta. We're just putting these cotangents alpha and beta at the corresponding entries of matrix L. If the hij is on the boundary, we only use the cotangent alpha. There are many ways to derive this Laplacian, but we would like to take a different approach. So assuming that vertex I is any interior vertex on the mesh, and we start by integrating the delta x within the wandering neighbor of vertex I. We can apply the divergence theorem, so the volumetric integral now becomes the boundary integral, the line integral. It will integrate over all edges highlighted in orange. Since this function is piecewise linear, after some computation, we will arrive at the same cotangent Laplacian. So this is really a standard one that you have seen everywhere in geometry processing. But so far nothing is new here. The only difference is that how we will address the boundary. So in case that hij is on the boundary, using the same derivation, but this time, if we only consider the contribution from the interior boundary, which is marked in orange, we will arrive at the cotangent Laplacian. So this is the usual one that you see everywhere in geometry besides if you only have this orange part. But we could be more careful with that. According to the divergence theorem, the contribution should not only come from the interior boundary that is in orange, but also from exterior boundaries that is in green. So only after considering these green edges do we have the closed boundary. And only in this case, we have the linear precision. So we can denote our new operator as K, which simply is standard Laplacian L plus the new atom N. The L is just the standard cotangent Laplacian that you have seen everywhere in geometry processing. And the additional term measures the normal derivative. The N measures the normal derivative along the boundary. Okay, so the similar idea applies to 3D as well. Here is the mesh that we will use in 3D. It is actually a tetrahedral mesh. So this could be one limitation of our method. We have to use tetrahedral mesh in 3D, and you know that the discretization could be very hard sometimes. Well, let's try out our new operator, applying the new operator K to the same linear function, and it outputs perfect zero even on the boundary of the domain. So linear precision is true for boundary vertex, and this is really what we are looking for. So we would like to point out that our new operator is no longer symmetric, which is not an issue because we are using the square Laplacian energy, which is still positive semi-definite. Using our new energy, the Armadillo transpose is reproduced on the right-hand side. Okay, let's look at some results. Previous method explores the idea of doing simulation at a cross-handle level, like a cross-mesh or some cage, and then using some interpolation techniques to upsample the fine details of the higher resolution mesh. This will achieve great performance boost without a much loss of deformation quality. So this method applies to both variational modeling and physical simulation. Our method also interprets high resolution mesh from a few control handles, and also it is suitable for this task. And we are even more flexible because we do not require any cross mesh or cage. Here is how we construct our cross handle structure. Besides user handles, we sample some auxiliary control points throughout the domain, like the purple points here. These auxiliary control points are only used to compute weights and are not directly controlled by the user. At runtime, they will be hidden from the user and will move automatically by minimizing a nonlinear energy. Yeah, again, you see the fast redefinition of control handles. Okay, so we explain the idea of subspace design in this simple example. First, with only two rigid handles, we bend the SIGGRAPH using a linear plane skinning with BBW weights. We see the familiar joint collapse artifacts. Like all linear methods, skinning with our method also suffer from the same artifacts. But these artifacts could be fixed by simply adding two extra control points. These two extra control points will move automatically by minimizing the nonlinear energy. Artifacts disappear in this case. So in this way, we can easily design a compact deformation space fixing the artifacts by simply placing the auxiliary points to where we want them to be. Previous spaces used in physical simulation, like harmonic modes, could suffer from their global nature. In this example, moving the right ear of the bulldog also affects the left ear, which is undesirable. In contrast, our method is the most suitable for the hard constraint and also interpolation. Our weights allows negative weights. we highlight that negative weights is essential to obtain fair deformations. In this example, we bend the rectangle into a half cycle using both non-negative weights and also our method. The non-negative weights results in ripples, and our method provides pretty good deformations. Using a dynamic energy, our method also supports subspace physics. In this example, the big body is controlled by a skeleton, and the user specifies the motion of the skeleton using keyframing. And we place some auxiliary control points on the body of the bunny. In this way, the user designs a compact subspace that is able to express the secondary motion effects due to inertia and gravity. Okay, now it's the live demo session. Oh, we can now see it. We have this nice seahorse. So basically you can see that there's some control regions and also some control points distributed on the belly and tails of the seahorse. So we can move it. So you see that although we only have a few degrees of freedom, the deformation looks pretty real. Right, so more interestingly, we can add control handles on the fly. Just click on where you want, and we can constrain the back of the seahorse. Right, and also sometimes you want to control the tail of the seahorse, just clicking on where you want. Yeah, here we go. Okay, let's back to the talk. And compared to previous method, we solve a much cheaper problem, just a linear problem, whose solver is highly optimized. So we are much faster than previous automatic scaling weights. In summary, our technique provides an efficient way of controlling deformations and also designing subspace. However, there are several limitations and also opportunities for future work. The first is that we always require discretization of input domain, which is hard. And this might suggest that the future work using boundary element method instead of our finite element approach. And we imagine that the similar techniques could be used to interpolate quantities other than deformation fields. And we would like to thank many friends for discussions and help, as well as our sponsors. Oh, it's going outside. And source code and demos could be found online. Thank you for your attention. That's all.